Welcome back, and in today's lesson we want to talk about pulse width modulation, usually just called PWM, and it's in what are called the output compare modules on your PIC. So let's talk a little about what we mean by PWM. Well, it's our old friend the square wave. It's simply a repeating square wave, and what we're interested in is the period, right? And how long it's on for. The on time is sometimes called the duty cycle time as well, right? And so this is a square wave that keeps repeating itself. So it's just digital output because it's either high or low with some sort of timing factor so that the on time and the off time are always come out correctly. Sometimes people give the duty cycle as a percentage, so it'd be the ratio of the on time to the total period. Okay, so something like 30% here, say. Anyway, let's move on. Some details of the chip. Well, there's 5 modules that can generate this continuous square wave. They're set and forget, which means once you set them, they'll continuously output that module signal without you having to do anything else, unless you want to change the signal. Okay? Now, the pins that output this signal are called OC1, OC2, and so on up to OC5. OC stands for output compare. There are no such pins in the pinout diagram, and what we have to do is to use the reprogrammable pins. And we've talked about that before, and I'll show you an example when I show you some code later. Why do we want to do PWM? Well, we've written an entire code recently that all it did was blink an LED. But that's kind of boring, and maybe you want to do other things, right? So you could certainly put an LED connected with a resistor to this pin, and the LED will blink. It will also play a tone on a speaker, and we'll talk about that later. But mainly, in most places, although not a lot in this class, it's used to control, like it would be used to control the speed of a motor, but also the color and brightness of an LED. Let's see how we would do this with an LED, right? Now, if the period is long, you can see your LED go on and go off. But if the period is short, the colors would blend, which is what we've already seen with a bicolor LED. I want to show you a couple of examples. Here is a little animated GIF, and it's pretty stupid. All it does is it shows a red rectangle and a green rectangle, keeps repeating. You should be able to clearly see the red and green rectangles. But if I give you a version where we do it much faster, you still see some red and green occasionally, but you also see, well, what looks orange or brown to me. If you did it properly, it might look a little fancier than that. But if you flash red and green together, you get something orangey or ambery or brownish. Okay? And we've seen that, hopefully in class already. Okay. Now, if instead of 2 colors, okay, you have a large duty cycle, then the LED, for instance, would be on most of the time, so it would be bright. On the other hand, if the duty cycle is small, then most of the time there's no power going through the LED, and the LED will be off most of the time, so it'll appear dim. We use the same thing to control motor speed. And what you have to remember about motors is that motors, when you get them spinning, first of all, it takes time to get them up to full speed. And if you stop supplying power to the motor, because of inertia, it takes a while for the motor to stop turning. Okay? And what that means, and we'll try to explain it in some detail in the next slide, that if you're using a short period signal, then if the duty cycle is small, the average speed of the motor will be lower than when the duty cycle is large. And if you want it, you could use 2 pins with the motor to control the direction of rotation, the same way we had used 2 pins to control the color of the bicolor LED. So let's look at the top of this slide. This is the behavior of an ideal motor. When the voltage is high, the motor is at full speed. You turn it off and the motor's to 0. It doesn't happen. Real motors have inertia. So it takes a while to get up to full speed, and when you turn off the motor, they take a while to slow down to 0. So instead of this nice square wave, right, what you get is something that looks like shark fins. Okay? Now, these examples have been shown with long period and a long on time. If you look at one of these shark fins and you think about having a small on time, the inertia over that time keeps you from getting to the full speed, right? And if you are at full speed and you suddenly turned off, right, you don't drop to 0 in that time. So if you use small periods, right, and a small on-off cycle, then what you will get was something that would look like this ripple signal. And it would average out to some speed in between 0 and maximum speed. So your motor speed is reduced. Controlling how much time it goes on for, the higher it would go. We'll also play around with sound generation. We are giving you little speakers, really cheap speakers, and a pure musical tone is a sine wave, but we're generating square waves. But if you send a square wave through a speaker, it'll make a noise. It might not be as pretty as if it was a sine wave, but it still makes a noise. Remember that frequency is 1 over the period. And if you wanted to play something like music, and you might remember me playing the chicken dance at the start of the first class, is you need to know the frequency of the notes. Okay? But they're easy to look up online if you're not musical and don't know that sort of thing already. Okay, so now we're actually going to talk about how the PIC generates sound. Okay? There's 3 elements that we need to talk about. The first element is the peripheral bus clock, the speed that the modules operate at. We'd been using the system clock at 8 megahertz, and usually the peripheral bus scale was 1:1, so the peripheral bus was 8 megahertz as well, but we could change either of those, right? And the second element that you need is the timer. The timer really is just a counter. It counts timer edges. Okay? And it's the timer that gives us TPWM, the period that we're interested in. The other element we want is the output compare in PWM mode, its counter. And what it gives you is the duty cycle. So in the example, what I'm talking above, the period is set to 5 units of whatever the clock speed is. And the duty cycle or on time is 2 cycles. So here's how it works. Here's the peripheral bus up here, this spiky thing, right? And we turn on the timer counter, and the timer counter starts at 0. Okay? And the timer counter is going to count up to 5. Well, actually it counts up to 4. 0, 1, 2, 3, 4. And then the timer rolls over and it starts counting at 0 again. So 0, right? 0, 0, 0. So in the PWM signal, communicates with the timer and always spots where it rolls over and goes back to 0. And it turns on, right? And that is what defines the TPWM period. All these guys are the same. It's the time between the timer rollover. Okay? Now, PWM has its own counter. And what this counter does is it looks at the timer counter, and when it gets to the duty cycle, in this case 2, it turns the signal off. Okay, so the clock counter is 0, turn on my signal. Sorry about my dog barking. She hears some noise. Right? Then, when the counter reaches 2, it turns the signal off. Signal stays off till the counter reaches 0 again, and the PWM signal comes back on until the PWM counter reaches 2 and it turns off, and it keeps repeating and repeating and repeating. Okay, how do we do that in code? Well, we're going to use the peripheral library functions, and I'm going to show you some examples. One is using what's called the 16-bit timer, and one with the 32-bit timer. A 16-bit timer gives you a shorter time than a 32-bit timer. That's all we're concerned about. Here's the code. Okay, so in this example code, I'm using timer 2, but I could use either timer 2 or timer 3. Those are two options. You'll notice the green here, where everywhere where it says 2, that's referring to timer 2. And so I am always using timer 2, right? But it all could be 3s for using timer 3. And I'm using output compare pin 1. And so the module for output compare 1. So here's my code for the timer. This is setting the period. This code right here, right, from here to here, this is the configuration. This is turn the timer 2 on, and here's the prescaler. We'll talk a little bit more about the prescaler a little later, but all this means is there is no prescaler, it's 1. Okay? And here is the period. 5 in the previous one. All right, so I decided to use 5 here. But it could be any number from 0 to 65535. That's 2 to the 16 choices, which is why this is a 16-bit timer. This prescaler can be 1, 2, 4, 8, 16, 32, 64, or 256. Right now, the counter is carrying every one edge, okay, counting 1, 2, 3, 4, 5. The prescaler just simply tells it to count by 2s, so every 2 edges, every 4 edges, or every 8 edges, what have you, up to 256. Those are all the possible choices. Okay? So this is simply giving me a period of 5 peripheral bus periods, TPB. Right? Now, in your code, the peripheral library recommends that you close the module before you open it. And the only reason for that is maybe leftover settings would be active. So closing the module first means they're all set to their default values. Here's how we set the output compare module to what we want. The 1 is for module 1, but we have choices of 2, 3, 4, or 5, right? Here, we're turning it on, and the only letters that you need to see in here is that we're using PWM. Okay, I skipped to 16, right? I skipped to 32, so I come back here. We're using mode 16, which means the 16-bit timer. And this guy is using timer 2 as the source. Okay? If I change this to 3, I'd need this to be 3. If I hadn't opened timer 3 and I had this as 3, we don't get any signal. Here, this number, that's my duty cycle. It's got to be a number less than my period, or we get 0, right? Or, sorry, the signal will be constantly on. This number is for a setting that we're not going to be using in the course, so you just leave it to 0. Okay? This last line, this is set the DC, or the duty cycle for the output compare 1, PWM. This is a fairly long line of code. This is just a shortcut. If later in your program you want to change the duty cycle, you just use this. You could use this guy again, but this is a little shorter to use. Okay, so that's the 16-bit code. Let me show you the 32-bit code. Okay, we have two 32-bit timers, but we only get to use open timer 2, 3. Okay. I'm using the same period, right? But I could use a much bigger period if I wanted, okay? Because we go to 2 to the 32 minus 1. The number of prescalers are all the same. The code down here, right, there's only one change. We're using the 32-bit timer. It's still timer 2, okay? And I'm still using the same duty cycle. There's no real reason with numbers as small as this to use a 32-bit timer, right? You'd only use the 32-bit timer if you wanted really long periods, okay? And the same code here for changing the duty cycle later, okay? Okay, so I'm now going to call up in some example code. Okay? Here is 16-bit PWM. Okay? So all my regular code here. We need to pick which pins are going to be the digital outputs. Again, we've got to look at the appropriate table to find out which pins we can use for OC1 and which ones for OC2. And once we pick them, right, we have to make sure those pins are digital outputs. Sometimes the modules ensure that happens, and other times they don't. So to be careful, I normally always set them in my code. Down here in this example, I'm using two different timers, but I could use the same timer. So open timer 2, I'm using a scalar of 2, and my period is 3000. Okay. Okay. Open timer 3, okay. And then here's the two pins being configured. OC1 uses timer 2, and the duty cycle is 22,000. So OC2, right, is using this guy because it says timer 3, and is using 8,000. After a 10-second delay in this code, I changed the duty cycle of this, okay, just to show I can do it. And this is a lot simpler to write than rewriting this with the 22,000 replaced by 5,000. Okay? Okay? That's how simple it is. Let's calculate what the period and on time are. So coming back here. Okay? Here are the two formulas from the book, the manual, that tell you about PWM. So the period for PWM is whatever the period timer is plus 1 times the prescaler times whatever the peripheral bus period is. Okay? So the peripheral bus period would typically be 1 over 8 million if you're using the settings I've always been using. Okay? So if we go back to the code, 30,000 plus 1 times a prescaler of 2 times 1 over 8 million. That gives you a period of 0.00750025 seconds. The on cycle was 22,000 times the same prescaler. The period was 1 over 8,000, so that's 0.055 seconds. Checking the code again, what the other numbers were, 20,000 and 8,000 here, going back to where we were, right? 20,000 plus 1, this much time. Prescaler is 4. 8,000 times 4 times 1 over 0.004 seconds. Okay, so that's how you do the timing. And you should see that I made a mistake earlier because I always forget about this one, right? So to have a period of 5, that guy really needs to be 4. Okay. Okay. So that's it. Okay. The basic code is fairly simple, right? Because most of the settings we don't have to set. The hard part is the opposite of this problem that you see before you. If you know the period and the duty cycle, these calculations are fine. Typically, you have to go the other way. I might ask you for something like a 200 hertz signal with a 30% duty cycle, and that takes more time for you to calculate. Okay? So going the other way, right? Asking for a particular frequency and duty cycle, that's where the harder calculations are. Take care for now.